Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by AVS Thipa. In the previous modules, we have seen the effect of charges at rest. We have seen distributed charges, one-dimensional charge, two-dimensional charges, and three-dimensional charges. We have also seen what happens because of a point charge and system of point charges. We have defined electric flux density, electric potential. We have also seen the difference between the electric fields in conductors and electric fields in dielectrics. In the current module, we would see the effect of charges at uniform motion. The charges at uniform motion are called steady currents. So in the current module, we would see the effect of steady currents. Let me tell you, the effect of steady currents is that it produces a constant magnetic field. The analysis of this constant magnetic field, which is produced by the steady currents, is called magnetostatics. Please understand that in magnetostatics, we will not analyze the effect of permanent magnets. In fact, in the entire EMT, we would never discuss the effect of permanent magnets. We would only discuss what happens if a current is passing through a conductor and what is the nature of magnetic field produced by it. We would see what would happen if the current is not static, it's not steady, if it is varying with time in the subsequent modules. But for the current module, we would limit our discussion to constant time independent magnetic fields. This effect of magnetic field being produced by steady current was first determined by Oersted. It is an experimental result which he got while working with currents and magnets. Before we understand the Oersted experiment, let us understand the concept of magnetic needle and magnetic compass. These are the magnetic poles of Earth's magnetic field. We all know that Earth itself has a magnetic field in it. The magnetic field does have two poles. Whatever is the magnetic field, wherever is the magnetic field, wherever a magnet exists, a single pole cannot exist. It should always be in pairs, a north pole and a south pole. Similarly, the Earth's magnetic field also has a north pole and a south pole. Now, if you place a compass here, the label north of the compass, north label of the compass would always point towards the north of the Earth's magnetic field, and south label of the compass would always point towards the south of the magnetic field. How does this happen? This is because of the property of magnetics that like poles repel and unlike poles attract. A magnetic compass is made of a magnetic needle. This magnetic needle would also be having two poles, a north pole and a south pole. This magnetic needle is so thin, it is so light that the effect of gravity in this is very low. So whatever this magnetic needle responds to, it responds to the magnetic fields only. Now, this north of the magnetic needle, in absence of any external magnetic field, would be responding only to Earth's magnetic field. Right? Now, so this north will be repelled by this north, and this south will be repelled by the south, and this north would be attracted by the south, and the south will be attracted by the north. So the magnetic needle would be aligning itself in this way. Now the magnetic compass has an environment set where a magnetic needle is placed in such a way that the gravitational force and also the other environmental factors does not influence this magnet. So wherever this south comes would be labeled as north, and wherever this north comes would be labeled as south. So that is how people used to navigate using magnetic compasses. Right now, so what we can understand is, if this is the case, the north is aligned with the label north is aligned with the Earth's magnetic north, and the label south is aligned with the Earth's magnetic south. That means there is no external magnetic field present. If there is an external magnetic field, there would be change in the orientation. So if there is change in orientation, that means there is an external magnetic field present there. If they do not change, that means there is no magnetic field. Right? So we can understand this from the compass. Now, let us go to the Oersted experiment and what he has done. So he has placed the magnetic compass over there, and he has taken a battery and he connected it to the conductor via a rheostat. The function of the rheostat is to vary the resistance offered. Right? And we have already seen while discussing the electric field in the conductors that when a potential difference, constant potential difference is applied, a constant current flows. Right? And all the electrons are connected here. That means the current would be in this direction. So what Oersted has observed is when the current is flowing in this direction, there is change in the orientation of the compass. So this indicates presence of magnetic field. Right? So what he did is he wanted to analyze this magnetic field which is present there. So he varied resistance and allowed more current to pass through it. So what he has observed is the deviation is much more. Then he has changed the polarity of the battery. That means the direction of the current also changed. When the direction of the current has also changed, the twist is now in the opposite direction. Earlier it was in this direction, now it has gone in this way. He has increased the current in the opposite direction, and again he has observed that the deviation increased in this direction. He has changed the position of the magnetic compass and has changed that the magnetic field produced is opposite on the either end of the wire. He has also observed that if the distance is increased, then the deviation is being decreased. So this experimental observation has clarified one thing, that a magnetic field can be produced by current. But he did not quantify anything. But later, two scientists, Jean-Baptiste Bayat and Felix Savart, has worked in the fields of this and has quantified that the magnetic field intensity produced at any point P by the differential current element. The meaning of differential current element is, for example, if this is the current carrying conductor, they could not quantify the magnetic field because of the entire conductor. Instead, what they have done is, if I consider the current flowing in this region, this has become the current element, differential current element. Because I have already told you, you may even remember that we would be able to understand or analyze only for point sources, and we would extend this analysis from point source to the continuously distributed sources. But any analysis is much more simpler if we consider point source. So this is a way of obtaining a point source from a conductor. So this point source obtained are called as differential current elements. So the magnetic field produced by this point is the differential magnetic field. The differential magnetic field intensity produced at a point because of this differential current element is directly proportional to the strength of the current element, and also the sine of the angle between the current element and the line joining current element to the point. We would see this graphically much later, but mathematically I can write them that dH is proportional to ideal, dH is proportional to sine alpha. So together I can combine them and write dH is proportional to ideal sine alpha, right? So this ideal is the current element. There are three different current elements possible. We would see about them in the later slides, but right now we discuss the magnetic field intensity. I have already told you that the magnetic field intensity strength decreased when we are moving away from the conductor, and the order of decrease is square. So it is inversely proportional to the square of the distance between the point and the current element. So dH is inversely proportional to 1 by r square. So together I can write that dH is proportional to ideal sine alpha by r square. To remove this proportionality constant, I would use, so to remove this proportion, I use a proportionality constant. dH is equals to k ideal sine alpha by r square. For SI units, the value of k is found to be 1 by 4 pi. So dH equals to ideal sine alpha by 4 pi r square. This entire thing discusses the magnitude of the magnetic field intensity, but the direction is given by the right hand rule. That is, you hold the conductor in your right hand, your thumb should point the direction of the current. If you curl your finger, the direction of the curl of your fingers indicate the direction of the magnetic field. So I can say that, for example, if we are talking about this point here, right, because of this source, this is ideal here and this is r bar. So your magnetic field intensity is normal to the plane containing this, because it is going into the plane. Similarly, if we are here, it is going out of the plane. Again, this is also normal to the plane containing this. So from the magnitudes and the direction, I can conclude that dH bar, the vector form of Wyatt-Savart's law, says that dH bar equals to IDL bar cross AR cap by 4 pi R square. This is the vector form. This is something you might be seeing for the first time. As I have told you, there are three differential current elements. They are defined depending on the conductor through which the current is flowing. Your regular current carrying conductor, that is a current through a wire, the current element is, as we have seen already, that is, if a wire is carrying current, the current element would be just making a point source out of it. So the current element is IDL bar. Understand that the units of this are ampere meter. Right? This is an interesting thing to discuss. What if instead of a wire from point A to point B, current is flowing through a strip of conductor? So this is node A and this is node B. Current is flowing in this way, but it is, instead of a conductor, it is flowing through a strip. You may see the strip conductors in your microprocessors, microcontrollers, and you may find its application in various antennas, and these strip conductors are also available in your mobile phones. But you may see that these are nothing but conductors which are in parallel. You may consider them to be the conductors in parallel. Only difference is they are not separable. They are all combined, right? They are not separable. They are of the same material. So to quantify the current from A to B, right? If, for example, if the current flowing through this is some I amperes, current is flowing from A to B, then the current flowing through at each unit is same, because this entire strip is made of same material and same potential difference is applied across them. So current flowing through any unit distance or any unit width of the conductor would be same. So current flowing through unit width of this strip conductor is called as linear current density, defined as K equals to I by W. Current passing through unit width of the conductor. So from this, I can always measure the total current through the strip conductor to be equals to the linear current density times the width. Now this is a two-dimensional body. The differential surface element of this surface is ds. I am talking about the scalar differential surface, not the vector differential surface element, where the vector is perpendicular to the surface. So this current element, because of current through a strip, is also a vector quantity where the direction of that vector is from A to B. That is the direction through which the current is flowing. So the current element is K bar ds. Again, its units are ampere meter, because the units of K are ampere per meter and units of the differential surface is meter square. So the units of the current element is again ampere meter. Again, this is a more common conductor type, that is current through a cable. Again, if you are connecting a conductor from A to B, but now instead of a strip or a wire, you are using a cable. You know that a cable is a three-dimensional entity where the inner layer carries conductor and the outer layer doesn't, right? Now this inner layer is a cylinder. the current is flowing through this cross-sectional area, right? So the current per unit cross-sectional area is defined as surface current density, which you have already seen. Surface current density represented by Z bar. Its direction would always be A to B. So the current element because of current through a cable would be Z bar dV. Again, its units are ampere meter. We have already seen, even in case of electric fields, we have determined the differential electric fields and then we have integrated them to get the total electric field. This is nothing but application of superposition theorem. This dH bar can be obtained from the expression of vector form of Biot-Savart's law. So the magnetic field intensity due to the current carrying wire would be this. This is just the line integral and the surface integral of the surface current element cross the vector joining the current element to the given point. Similarly, for a cable or a solid conductor, it is the volume current density, volume current element, three-dimensional current element crossed with the vector joining the current element to the given point and volume integral. So these are three different ways to find out the magnetic field intensities because of three different setups. But now let us see the first setup, current flowing through a wire. And the magnetic field intensity because of the current carrying wire, to determine that, let us consider a conductor which is aligned itself with the z-axis. Its endpoints are from H1 to H2. Consider a point 0, 0, H dash. Let us assume this to be the point source which we are considering for our analysis. That means this should vary to give us the current element. So the current element would be I dH dash along AH gap. Now the point which we are considering be rho, phi, h. If rho, phi, h is the point in consideration, the vector joining the current element to the point is comprised of two components. One of them being this and the other being this. This is the perpendicular from z-axis, that is a rho cap, and this is the negative z-axis, that is minus az cap. The magnitude of this is h dash minus h and the magnitude of this is rho. The angle this r bar is making with the current element is alpha. So r bar equals to rho times a rho cap minus h dash minus h ah cap. And the angle the vectors from the endpoints are making with the conductor be alpha 1 and alpha 2. I will be needing them because instead of solving them in terms of h, I will try to solve this problem in terms of the angle. You'd see what I mean in the next slide. So the magnetic field intensity because of the current element is integration of the differential element, a differential magnetic field over the limits of h1 to h2. Here you may observe that instead of arrow cap, I have written r bar by mod r, thereby giving the numerator to be 4 pi r cube. Now I have my ideal to be I dh dash ah cap, and I have my r bar to be rho a rho minus h dash minus h ah cap. Now if I cross them, you may see that cross product of like vectors would be 0, so I would be remained with only this term. But from the relation between unit vectors, which we have discussed in the previous slides, previous modules per se, I can write that ah cap cross ar arrow cap to be equals to a phi cap. So my numerator term is this, whereas denominator r is nothing but the magnitude of r bar. I can calculate them using root over of x square plus y square, and it is cubed, hence it is x square plus y square to the power of 3 by 2. I hope all the terms here are clear. So what I have is to convert this h1 h2 to alpha 1 alpha 2. For that I need the relationship between change in the h dash to change in alpha. If I do that, because of the right angle triangle between h dash minus h, rho and r, I can say that h dash minus h is r cos alpha. Similarly, rho is r sin alpha. From this I can say h dash minus h by rho is cot alpha. Therefore h dash equals to h plus rho cot alpha. So dh dash is equals to dh plus d rho cot alpha, in that dh is not changing as long as this point is not changing, and we are calculating the magnetic field intensity at this point only, hence dh is 0. So dh dash is equals to d rho cot alpha plus rho times d cot alpha by applying uv. Again, this rho is not changing as long as this point is not changing, hence this is 0. So I am remaining with dh dash is equals to rho times d cot alpha, which is nothing but minus rho cosecant square alpha d alpha. So the relationship between change in h dash and angle is dh dash is equals to minus rho cosecant square alpha d alpha. Right? So this is the expression we have, and now I am trying to represent them only in terms of rho and alpha. Again, I am left with this r cube. This r cube, I have already seen that rho by r is equals to sin alpha, hence r equals to rho cosecant alpha, hence r cube can be written as rho cube cosecant cube alpha, and this rho and this rho can be multiplied, so the numerator can also be written as, this negative is taken outside, rho cosecant alpha whole square, and the denominator is rho cosecant alpha whole cube. When I cancel them, I am left with rho cosecant alpha in the denominator, but 1 by cosecant alpha is nothing but sin alpha, so I can, my integration turns to minus alpha 1 to alpha 2 I sin alpha by 4 pi rho d alpha a phi cap. Here again, sir, you may understand that the integration of sin alpha is minus cos alpha, integration of minus sin alpha is cos alpha. So when I integrate this over the limits of alpha 2 and alpha 1, I will be remaining with 1 by I by 4 pi rho cos alpha 2 minus cos alpha 1 along the direction of a phi cap. So this is the value of the magnetic field intensity at a point where alpha 1 and alpha 2 are the angles the vector joining endpoints is making with the current carrying conductor. Because these are cos alphas, it does not matter whether I measure the alphas clockwise or counterclockwise. Now, what would be the magnetic field intensity of a current carrying wire of infinite length? The meaning of current carrying wire of infinite length is the endpoints H1 and H2 are now H1 equals to negative infinite and H2 is equals to infinite. So when H2 is infinite, what is the value of alpha 1? And when H1 is negative infinite, what is the value of alpha 1? And what is the value of alpha 2 is what we should be worried about. So to do that, let me look at this and understand from the expression that h dash minus h by alpha equals to, sorry, h dash minus h by rho equals to cot alpha. I can say alpha equals to cot inverse of h dash minus h by rho. So when alpha 1 equals to cot inverse of h1 minus h by rho and alpha 2 equals to cot inverse of h2 minus h by rho. So for one h2 to be infinite, alpha 2 is equals to cot inverse of infinite minus h by rho, that is cot inverse of infinite, cot inverse of infinite, that is cot inverse of something k by 0, that is sine inverse of 0 and cos inverse of some positive value. The answer is alpha 2 is equals to 0. Right? And what happens to the value of alpha 1? Alpha 1 is equals to cot inverse of h1 minus h by rho, that is alpha 1 is equals to cot inverse of minus infinity minus h by rho, that is cot inverse of minus infinity, that is cot inverse of some negative number by 0, that is sine inverse of 0 and cos inverse of some negative number. The answer to that is readily pi. Understand that this is not alpha 2, this is alpha 1. So alpha 1 equals to pi and alpha 2 is equals to 0. So if I substitute them here, my magnetic field intensity would be 1 I by 4 pi rho 1 minus of minus 1 along a phi cap. This 1 minus of minus 1 is nothing but 2. So my answer is I by 2 pi rho a phi cap. This is the magnetic field intensity because of an infinite length of current carrying conductor. Now imagine a current carrying conductor of infinite length, just like what we have done. Determine the circulation of magnetic field intensity around a circular path. Here it is along a circular path around this conductor. What I want to determine is this. But the meaning of circular path, if I have a conductor here, the circular path around this conductor means the perpendicular distance is constant. The perpendicular distance rho do not change. Because I am talking about the circular path, the value of h do not change and the value of phi ranges from 0 to 2 pi. we know that for infinite length of current carrying conductor, the magnetic field intensity is I by 2 pi rho a phi cap. We have already seen that. And from the discussion of differential elements in cylindrical coordinate system, dl bar is equals to d rho a rho cap plus rho d phi a phi cap plus dh ah cap. In that, dh is 0, d rho is 0, so dl bar is just rho d phi a phi cap. When I dot these two, a phi cap and a phi cap on both same directions, so the dot product would be 1, rho and rho get cancelled, I by 2 pi is constant. If I take this outside the integral of d phi is phi over the limits of 0 to 2 pi, the answer would be I, because it would be 2 pi and 2 pi gets cancelled, only I is remaining. Okay, my question to you is, do the same problem, but instead of a circular path, determine for a rectangular path and tell me if the answer change from this to anything else. One hint to you is Ampere's has already done that, and Ampere has discovered that the circulation of a magnetic field around a closed path is equal to the net current enclosed by the path. That is, if you take a circle like this, okay, now you have to follow your right hand rule, and you should curl your fingers in this direction. So if you curl your fingers in this direction, the thumb would be pointing in this direction, right? So the circulation of the magnetic field intensity along this path would be same as the current flowing in this path. This is called as the current enclosed by the loop. The meaning of current enclosed by the loop is, if you have a circle, whatever current is passing through this loop, that would always, they are all be considered as the current enclosed by this loop. Okay, the mathematical representation of Ampere circuit law is integral of h bar dot dl is equals to I enclosed. I would stress to emphasize on that point of current enclosed by considering the following example. Consider 8 conductors which are given below. This is node 1 and this is node 2. Some conductors are carrying current from node 1 to node 2, and some conductors are carrying current from, okay, let us not say node 1 and node 2, direction 1 and direction 2, right? Some conductors are carrying current in direction 1, and some conductors are carrying currents in direction 2, right? Now, if you consider a circular path and you determine the magnetic field intensity because of this, so you would have to curl your fingers in this path. So when you do that, the answer would be equal to the current which is flowing in this direction. So for in this case, the answer you would be getting is, in this current, 42 minus 40, that is 2 amperes. Similarly, if you consider another path and you try to determine the circulation of magnetic field intensity because of this, if you curl your fingers in this direction, it tells us the thumb points in this direction, so we will get the current flowing in this direction, but actually the current is flowing in this direction. So the answer you would be getting is 2 plus 25, 27 minus 27 amperes. That is the meaning of the Ampere's circuit law. We would see how this Ampere's circuit law can be used to solve the problems of magnetostatics in the next module. Till then, if you have any queries in this module, please ask in the comment section, and these are the references for which you can follow. This reference is for Oersted's experiment, and this is our reference textbook which we follow always, and this is the reference for right hand rule. Thank you. Meet you in the next module.